The second approximation method we're going to discuss is perturbation theory. So perturbation theory is the idea that we can take something with a known solution and make a small change to it, and then find energies and wave functions from that. So the small change, this is what we refer to as a perturbation. So let's look at an example. I think it makes more sense if we do that. So let's consider, let's say we have a particle in a box. We'll stick with a one-dimensional example to keep this straightforward. Right? And let's say we want to find instead, what if the box isn't just flat at the bottom, but it's sloped? Right? So the potential energy isn't strictly zero, but it increases linearly across the bottom of the box. This slope is a perturbation, because we can take a known system that we have and then add this perturbation onto it, and perturbation theory tells us how we can use that known system with the perturbation to find the new values. So we can still write our Hamiltonian and our Schrödinger equation, h psi equals E psi, and we'll split h up into two parts. So we will have the unperturbed Hamiltonian, H0. So this would be for our ideal system. So in this case, this would be the particle in a box Hamiltonian. And then we have our part of the Hamiltonian that's the perturbation. So we call that H1. So in the example we have here, this would be the slope in the box. All right, and so for this to work, the perturbation has to be small. I'll say that in quotes because it's not very well defined, but small in comparison to the original Hamiltonian, the H0. All right, and so we can also write our wave function. We can write it in multiple parts too. So our total wave function is this, and we have the zero order wave function, that's our unperturbed wave function. And so these would be the wave functions we'd have from our known system. And then we have corrections to the wave function. And this is a potentially infinite series. And so we call it, and same thing for the energies. So we'll have the total energy, we have the unperturbed energy of the known energy of our system, and then we have corrections. So first order corrections, second order corrections, etc. So these terms out here and here, these are corrections to our unperturbed system. Okay, so this is sort of how we set up our perturbation problem. And really what we're after, we know the zero order terms. We know H0, psi 0, E0, right? These, by definition, by the way we set up our problem, we know what these values are. And we want to find the corrections. So H1 is part of our definition of our problem, but we also want to find, say, our wave function corrections and our energy corrections. Now we can look at these up to an arbitrary number of corrections, but we'll look at just the what we call the first order corrections. So where we just look at the first possible corrections to the wave function and the energy. So this is known as first order perturbation theory. In practice, usually at least second order is done in computational chemistry, but since we're doing this by hand, we'll just look at the first order corrections.